Okay, today we're gonna continue to talk about functions, specifically linear functions. Just to kind of give a broad base, there are 8 different types of functions. So there are linear, quadratic, rational, power, polynomial, exponential, logarithmic, and sinusoidal. So our focus is going to be on linear functions and or equations. And in math, like when you have, all of these different families underneath functions, they're going to have the basic characteristics of a function, meaning that each input is going to match up with exactly each output. Their graph is going to be able to pass the vertical line test. Their table should be able to pass the X no repeat test. And their mapping should be able to pass the one arrow test. That's going to be true for all things that are called a function. And then underneath that, there's going to be some additional characteristics that go along with each one. So today, and our focus really for this whole unit is going to be on linear functions and what characteristics they have to be possessed to be classified as linear functions and or equations. So these characteristics can be seen when we're examining the different representations. Okay, so the graph of linear functions in our equations will be a straight line. And one way I always remember this, if you think of the word linear, right there is the word line. First word, line, line. The table of a linear function in our equation will display a constant rate of change, which is more commonly known as slope. Okay? So those are just kind of like the beginning things about functions in general and linear functions, which we're going to be studying. So if we go on to the next slide, so the most basic linear function in the family of all linear functions is called, you got it, the parent function. We all have a parent, at least one, most likely two. The equation of the linear parent function is f of x equals x. In other words, our output is going to be equal to the input that we put in. So imagine, almost like a broken machine. You put in one comes out. You put in two comes out. Okay. And we can write that another way called y equals x. This is important because a lot of times when we're talking about linear relationships, we don't always write them in function notation, right? This is the function notation when we say f of x equals x. So one thing we should notice, the x's are the same here, but that f of x and y are interchangeable. They're basically both considered the outputs or the dependent variable of the situation. So what does that look like in terms of a table and what we often use to write linear functions, relationships, when it's not in function notation like up here, is something called the slope-intercept form. So we're going to look at the parent function, this f of x equals x, otherwise known as y equals x, and what that means in terms of its table and how we would write that in slope-intercept form. So how would we write that when it's not in function notation? And not just the parent function, but all functions or all linear relationships. First off, if we're given an equation and we're asked to generate a table, essentially we're given inputs, or we might even be asked to decide on the inputs. And we should know from our study of evaluating functions that we can put those inputs into the function and determine the output. So for the parent function, if I put in 2, my answer is going to be 2. So in this case, when I put in -2, my answer is going to be -2. Decrease that just a little bit. When I put in -1, my answer is going to be -1. If I put in 0, my answer is going to be 0. If I put in 1, my answer is going to be 1. When I put in 2, my answer is going to be 2. So slope-intercept form we need to know is y equals mx plus b, where we already know that y is equal to the f of x, but m, this influencer in front of the x, we call that the slope or rate of change. And b is considered our y-intercept, also known as our starting point. Now, when you think intercept, think of interception in football. It's like where something is going to cross over. Starting point, well, you usually start at 0, right? So what happens when, what's the value of y when x is 0, right? That's what we're talking about. And the slope is what's our constant rate of change. Here, we can see that our rate of change is as our input grows, our output grows by the same amount. So from -1 to 0, we increase by 1. And from -1 to 0, we increase by 1. Increase by 1, increase by 1, increase by 1, increase by 1. So if you look up here, the reason why we don't see like an M is it's 1, right? So another way we could write that is we could have a 1 right in front of that x, and it would still have the same meaning as just x. The reason we don't put the 1 is because anything multiplied by 1 is itself. So that's why we just leave it as an x, and it's one of those assumed things in mathematics that what's lying in front of it is the coefficient of 1. So what does this look like as a graph? Well, we built a table. To make the graph, we just mark those points, and then we can connect those points using a line. Because just as I put in -2 and got a -2 out, if I put in -1.5, I get -1.5 out. If I put in -0.5, I get -0.5 out. If I put half in, I get half. If I put 1.5, I get 1.5. So these are just particular points, but I have to account for all the things in between because it's not telling me that these are the only possible inputs. I made those inputs in the table and I determined the outputs. So what would that look like? If I graphed these points on the graph, let's go ahead and mark 2 and -2. I'm going to insert, go down a little bit. I'm going to insert a shape, a circle, and I know that 0 and 0 is 1. And I'm going to color that blue so it's a little bit more noticeable. If I click off, I can see it. So here I'm going to click on it and actually fill it with blue. Make it look a little bit more square. Now, once I have one point, I'm just going to use the same one and I'm going to duplicate it. So I know 0, 0 is a point. I know based on my table That 1, 1 is a point, so I'm going to grab this point. Let's give me the cursor, and I'm going to move it to 1, 1. I'm going to duplicate it again, and I'm going to move it to 2, 2. Actually, I'll move it to -1, -1. And realistically, I can have it at 3, 3, 4, 4. All of these can represent inputs. So I'm going to select a line. I'm going to do an arrow. And what we would find is our graph would go through the complete angle like this. Go so we can see. So this is what the line of the parent graph would do, and that's based on the equation that looks like y equals x, or f of x equals x. So what happens when I make changes to that? That's what I need you guys to explore in your guided practice. Okay, so next page, you're going to be comparing stuff. I've given you different functions. You need to build the tables. So here, if I put 1, or if I put the -2 in for x, -2 plus 3 would give me 1. So I'd go in here to this box, and I would put 1. And I'm going to go through and find all of those, and then I'm going to build my points on here, connect the lines. And then lastly, you need to compare what you have to what the parent graph is on the slide beforehand. Now, when we want you to compare, we want you to say what's the same and what's different, right? And primarily what's different, because they're both going to be lines, because if they're linear, they're both going to be lines. So what's changed? How has this line moved or been affected by what we've done to the equation? Here we added 3 to the parent function. What happened? What happened to the graph by adding 3? Here we multiplied by 3. So what happens to the graph then? Describe it as best you can down here in the compare section after you build your tables and your graphs. And this is just the start of linear functions.